Here's another multiplication cryptarithm. The 3-digit number ABC, when multiplied with the 1-digit number C, yields the product DBC. We need to reconstruct the digits that are being represented by the letters A, B, C, and D. As in the previous multiplication cryptarithm, we need to start with some letter, one of these letters A, B, C, D, and enumerate all possible values that it can take. And for each possible value for that particular letter, we need to look at what values can the other letters take in order to result in a valid multiplication operation. So in the previous multiplication cryptarithm, we decided to start with the letter A. We decided to enumerate all possible values that letter A can take, and for each possible value we try to infer what could be the values of B and C in order to make the overall multiplication operation a legal operation or a valid or a correct arithmetic exercise. And we saw that A could take only one of those values, which was 3, because only with A equal to 3 could we find values for B and C such that the overall operation was a valid arithmetic operation. In the same way, we now need to start with some letter whose values we will enumerate, and for each of those values we'll try to see what are the values that the other letters can take. So the question is, which letter should we begin with here? Well, A appears once, D appears once, B appears 2 times, and C appears 3 times. So maybe we can start with a C. And another reason why we might want to start with a C is that the very first step in this multiplication operation would be that we would be multiplying this letter C or this digit C by the same digit, and in the result, that is in the number that is represented by C times C, that number would have the letter C in the units place. So this particular property allows us to narrow down the possible values that C can take. So let's see, what are the values that C can take? So can it take the value of 0? Can C be 0? Well, if C is 0, then this 3-digit number would be multiplied with a 0, and the result cannot be a 3-digit number. The result would have been a 0. So certainly 0 times 0 over here would result in a 0 in the units place, but if you look at the effect on the overall operation, the effect is that the entire result needs to be 0 here, because you're multiplying this number with a 0. So we cannot have a 3-digit number in the result. The result should have been a 1-digit number, 0. So this is clearly not allowed. C cannot be a 0. Can C be a 1? Well, if we put C as 1, we get AB1 times 1, yielding the product DB1. Now if you look at this particular encoding, you'll find that it doesn't make sense, because AB1 times 1 should have been an AB1, but the result is a DB1. And the fact that we have a letter D here, not the letter A, means that the number or the digit being represented over here is different from the digit being represented here. So C cannot be a 1, because if C was 1, the result should have been an AB1. The hundreds place should not have had a different letter. Can C be 2? Well, if C was 2 here, then 2 times 2 would have been a 4. So these two C's would have been a 2, but the result of multiplying 2 with 2 would have been a 4. So there should have been a 4 in the units place, but since C was 2, we cannot have C being 2 and C being 4. So C cannot be a 2. For the same reason, C also cannot be a 3, because 3 times 3 here would have yielded a 9 in the units place. And C cannot be both a 3 and a 9. Can C be 4? 4 times 4 would be 16, and we would have a carry of 1 from that operation, and in the units place we would have a 6. So we would have C being equal to 4 in these two places and C being equal to 6 over here, which is not possible. So C cannot be a 4. Can C be a 5? Well, 5 times 5 would be a 25, and certainly 25 would have a 5 in the units place, so that's allowed. So it does look like C can be a 5. So if C was put to be equal to 5, we would have AB 5 times 5 being equal to DB 5. So let's see if we can choose values for A, B and D to make this multiplication operation a valid operation for some numbers. Now what you notice from here is that there is a 3-digit number AB5 being multiplied with a 5, and the result is also a 3-digit number, but the first digit is different. Now what are the possible values that A can take? Note that the result has to be a 3-digit number, which means A cannot take values like 6, for example, because if this number was 600 something, then if you multiply that number with 5, we would have a result that would at least be 3000. And if the result was at least 3000, it would need to have 4 digits, not 3 digits. In fact, A cannot even be 2. A cannot be any digit greater than or equal to 2, because if you have a number that's larger than 200, when you multiply that number with a 5, the result would be at least 1000, which means the result should have at least 4 digits in it. So the only possible value that A can take is 1. A can only be a 1. A cannot be a 0, because we cannot have a 0 in the we cannot have a leading 0 in any number. So A must be a 1. So let's substitute A equal to 1 in this encoding and see what we get. We have a number 1B5 being multiplied with a 5, and the result is DB5, where we know that D cannot be equal to 1 because we have already put A equal to 1. In fact, D also cannot be equal to 5 because we have put C equal to 5. And similarly, B also cannot be a 1 and it cannot be a 5. So what are the possible values that B and D can take? Well, let's see. 5 times 5 here would be a 25. So we have a 5 in the units place, and we would have a carry of 2. When 5 is multiplied with B and when 2 is added to that result, we again get the digit B in the units place, in the tens place here. So what are the possible values that B can take which will allow this to happen? If B was 0, 5 times a 0 would be a 0. 0 plus 2 would be a 2. So we would have a 2 here. That's not possible because we just put B to be equal to 0. And B cannot be both a 0 here and a 2 here. It should have the same value everywhere. So B cannot be a 0. Can B be a 1? Well, if B is 1, then 5 times 1 would be 5, and 5 plus 2 would be 7, which means this digit needs to be a 7. But we just put B equal to 1 over here, which means B cannot be a 7 here. So B cannot be a 1. B cannot possibly take a value of 1. Let's try putting B equal to 2. Let me just write this down here. If B is put to be equal to 2 over here, then 5 times 2 would be 10. 10 plus 2 would be 12. And the way we would write 12 is we would write a 2 over here with a carry of 1 in the next place value. Now we put B equal to 2 over here, and we did get B equal to 2 over here. So we get a consistent value of B here and here. So that means we can legitimately put B equal to 2 over here. In fact, let's see what happens if we do that. We get 125 times 5, and if we evaluate this multiplication operation, 5 times 5 is 25, 5 times 2 is 10, 10 plus 2 is 12, 5 times 1 is 5, plus 1 is a 6. So if B has to be put to be equal to 2, then we automatically get a value for D, which would be 6. So in fact, we got a solution to this cryptarithm. We put C equal to 5, and then with that particular value of C, we got A equal to 1, and with A equal to 1, we try to enumerate the different possible values for B, and for B equal to 2, we got a legitimate multiplication operation provided D is equal to 6. So one possible solution to this cryptarithm is 125 times 5 is 625. This is one of the solutions. But again, some of the cryptarithms could have multiple solutions, so we need to enumerate the other possibilities as well. Now we were enumerating different values for B here. We had put B equal to 0, B equal to 1, and B equal to 2, and we saw that for B equal to 2 we get a legitimate mathematical operation, legitimate multiplication operation. Let's now put B equal to 3 and see what we get. If B is equal to 3, then we know that 5 times 5 would be a 25, so we would still have a carry of 2 into the tens position. And then when 5 is multiplied by 3, over here, the product would be 15. 15 plus 2 would be 17. So we would write a 7 over here and a 1 and a carry of 1 propagated to the next position. So if B is 7 over here and if B is 3 over here, that's clearly not consistent. So B cannot be a 3. Can B be a 4? Well, if B is a 4, then 5 times 4 would be 20. 20 plus 2 is 22. So we would write a 2 in the units place and we would propagate a carry of 2 into the next column. So if B is put as 4 over here, then we would get B equal to 2 in the result. And that's clearly not consistent. B cannot be a 4 here and a 2 here. So that's not allowed. Can B be put as 5? Well, B cannot be put as 5 because we have already put C to be equal to 5. So we cannot have two different digits being mapped to the same, we cannot have two different letters being mapped to the same digit in a cryptarithm, and so B cannot be a 5. What about 6? Can B be a 6? Now remember that when we got D equal to 6, this was when we had put B equal to 2. So when we move to a different value of B, now when we put B equal to 6, we are clearly going to get a different value for D, if at all we get a legitimate value for D. So let's not confuse this with, let's not assume that, we have to be careful not to assume that because we are putting b equal to 6, um, and because we got a d equal to 6, that we are not allowed to put a b equal to 6, because this d equal to 6 was with a different value for b. So what happens if we put b equal to 6? 5 times 6 would be a 30. 30 plus 2 would be 32. How would we write 32? We would write a 2 in this position and we would propagate a carry of 3 into the next column. Now if b is to be equal to 2 here and b is equal to 6 here, that's not consistent. What if b is equal to 7? If b is 7, 5 times 7 would be a 35. 35 plus 2 would be 37. And the way we would write a 37 is we would write a 7 in this position and we would propagate a 3 into the next column. Now if b was put as 7 here and if b was put as 7 over here, that is consistent. So in fact it looks like we can put b equal to 7. Let's try doing that and find out what value of d we get this time. If at all we get a legitimate value. It's possible that we may not get a legitimate value for d, in which case this would not really be a solution to the cryptarithm. So if we put b equal to 7, we get 175 times 5 is equal to db5. So let's actually do this operation and see whether we can map it to this format. 5 times 5 is 25. 5 times 7 is 35. 35 plus 2 is 37. 5 times 1 is 5 and 5 plus 3 is 8. So we get 875 as the result. Now b is equal to 7 over here as we wanted it to be. Now d is the digit in the hundreds place, which happens to be 8 over here. So that is a legitimate value for d. So we found another solution to the same cryptarithm, which is the exercise that we get when we put a equal to 1, c equal to 5, b equal to 7 and d is equal to 8. And the solution is the following multiplication exercise. 175 times 5 is 875. This also satisfies this particular encoding. So there are two solutions we have found so far for this cryptarithm. Let's see if there are any more. If we put b equal to 8 now, we get 185 times 5 over here. So 5 5s are 25. 5 8s are 40. 40 plus 2 would be a 42. And the way we would write a 42 is we would write a 2 in this position and carry a 4 into the next column. So if b is 8 over here, it would need to be a 2 over here. And that's not possible because we cannot have the same letter taking two different values. So b cannot be an 8. What about 9? Can b be set to be equal to 9? If we have 195 times 5, we would have 5 times 5 being 25, 5 times 9 being 45, 45 plus 2 would be 47, and the way we would write a 47 is we would write a 7 in this position and carry forward a 4 into the next column. So if we write b equal to 7 over here and b equal to 9 over here, that's not consistent. So b cannot be equal to 9. So for this particular value of c, for c being equal to 5, we found two different valid solutions to the cryptarithm, or two different possible combinations of values for the letters a, b and d, which are given over here. Let's now move to the remaining values for C. Can C be a 6? Well, 6 times 6 would be a 36. So it does appear that C can be a 6 because at least this particular column would not have a problem if C is set to be equal to 6. So let's go with that option, and we rewrite this cryptarithm over here. ABC times C is DBC, and if we put C equal to 6, then we get AB6 times a 6 is DB6. Again, we can see that A can only take a value of 1 over here. A cannot be a 0 because there cannot be leading zeros in our numbers. And A cannot be any digit greater than or equal to 2 because even if A was equal to 2, this number would at least be would be larger than 200. So if this number is larger than 200, the product of this number with 6 has to be larger than 1200. And if it's larger than 1200, then there should be at least 4 digits in the product. They cannot be just 3 digits. So A can only be a 1. So with A equal to 1, we can represent this same multiplication exercise as 1b6 times a 6 is db6. Now 6 times 6 is 36, so we write a 6 here and we carry a 3 into the next column. Now let's enumerate the different values that B could take. Can B be a 0? Well, if B was put to be 0 over here, 6 times 6 would be 36. 6 times a 0 would be a 0. 0 plus 3 would be a 3, and we would put a 3 into this particular position. So B would be set as 3 here, even though it was set to be 0 over here. So B cannot be both a 0 and a 3 in the same in the same exercise. So B cannot be a 0. What about 1? Can B be set to be equal to 1? Well, 6 times 1 would be a 6. 6 plus 3 would be 9, and so B would be set as 9 in this result. So if B is set to be 9 over here and B was set to be 1 over here, that's not consistent. What about B equal to 2? Well, 6 times 2 would be a 12. 12 plus 3 would be 15. So we would put B equal to 5 over here and carry a 1 forward. So if B was set to be 5 here and B was set to be 2 over here, that's not consistent. What if we put B equal to 3? Is that legal? 6 times 3 would be 18. 18 plus 3 would be 21. So we would have a 1 appear in this position. So B would be set as 1 over here, even though it was set to be 3 over here. That's not consistent because B cannot be a 3 here and a 1 here. Can B be set to be equal to 4? 6 times 4 would be 24. 24 plus 3 would be 27. So we would put B equal to 7 over here if B was put to be 4 over here. So B cannot be a 4 here and a 7 here. So B cannot take a value equal to 4. What about B equal to 5? Is that legitimate? Let's see what happens when we put B equal to 5 over here. In that case, 6 times 5 would be a 30. 30 plus 3 would be 33. And the way we would write 33 here is we would write a 3 over here and carry a 3 into the next column. So if B had to be set to be 3 over here when it was set to be 5 over here, that's not a consistent position because B cannot be a 5 here and a 3 here. Let's see if b can be equal to 6. 6 times 6 would be 36. Well, actually, we don't even need to do that. B cannot be equal to 6 because we already put C equal to 6. In fact, we didn't even need to test if B could be equal to 1 because we already put A as 1. So we can discard this possibility straight away. What about 7? Can B be set to be equal to 7? 6 times 7 is 42. 42 plus 3 is 45. And the way we would write a 45 here is we would write a 5 in this position and a 4 would be carried into the next column. So if B is set to be 5 over here when it was already set as 7 over here, that's not a consistent position, and so we can discount this possibility. What about B equal to 8? 6 8s are 48. 48 plus 3 is 51. So we would need to put B equal to 1 over here if B was set as 8 here. That's not consistent. B cannot be an 8 here and a 1 here. What about 9? Can B be set as 9 over here? 6 9s are 54. 54 plus 3 is 57. And the way we would write 57 is we would put a 7 over here and carry a 5 forward into the next column. So if B is set to be 9 over here, it would need to be set to 7 over here. That's not consistent. So in fact, we don't get any legal value for B if we put C equal to 6. So let's go back and enumerate the other possible values for for C. Can C be equal to 7? If C was equal to 7 over here, 7 times 7 would be 49, and the way we would write a 49 is we would write a 9 over here and carry forward a 4. So if C was set to be 7 in both these places, it cannot be set as 9 over here. So C cannot actually be 7. Similarly, C cannot be 8 because 8 times 8 would be 64. So this C would be equal to 4. And we cannot have C being equal to 8 in two places and being equal to 4 in a third place. So C cannot be an 8. Can C be a 9? Well, 9 times 9 would be 81, and we would write 81 by putting a 1 in the units place over here, which is contrary to the position that C is equal to 7. That C is equal to 9. C cannot be a 9 in these two places and a 1 in this place. So this is also not consistent. So in fact, the only two solutions to this cryptarithm that we found were these two, and both these had C being equal to 5. So this is possible, but none of these other possible values of C led to legal values for the other letters. We always ended up with some kind of a problem or a contradiction. So the solution to this cryptarithm would be these two exercises, or these two assignments of values to the letters A, B, C and D.